je suis très heureux d'avoir Daniel Merkle comme un intervenant pour la deuxième conférence dans notre cours. Daniel est un informaticien qui a étudié à Karlsruhe et il est un homme des algorithmes. Pendant son PhD, son doctorat, il a travaillé beaucoup avec des algorithmes distribués, répartis, comme les fourmis, des algorithmes qui sont inspirés à la biologie. Et après, il est allé à Leipzig, où il a travaillé plus dans la bioinformatique. Et après Leipzig, il a changé une deuxième fois complètement son orientation vers la chimie et en collaboration avec de différents chercheurs scientifiques, en particulier à Leipzig et à Vienne. Il a développé un logiciel, une plateforme qui s'appelle Merkle pour la réécriture graphique des molécules pour représenter la chimie et les réactions, les règles de la chimie. C'est très intéressant, je crois, le développement parallèle entre la biologie et la chimie, parce que la biologie récemment est devenue une biologie de système où l'attention c'est bouger d'un point de vue où on étude des protéines, une seule protéine, une protéine par protéine, et on a passé à étudier des systèmes de protéines et de régulation. Et c'est la même chose qui se passe dans la chimie un peu. Si vous êtes un chimiste organique et vous êtes très intéressé classiquement à la synthèse d'un produit, et la synthèse, c'est un peu une approche à la chimie réaction par réaction, parce que vous cherchez d'établir, de construire une molécule, et alors vous trouvez les réactions, la séquence de réactions. C'est comme éprouver un théorème, un peu, un pas de synthèse, un trajet de synthèse, c'est comme prouver un théorème un peu. Mais avec Daniel, la chimie a pris un peu une orientation plus systémique, où on étude pas une seule réaction en isolation, mais l'intérêt s'oriente vers un ensemble de réactions qui constituent un système et les propriétés de ce système. Et il faut une mathématique, une approche informatique pour analyser les propriétés de ce système et les générer en particulier. Et avec ça, je suis très content de vous donner Daniel.
So this work that you see here is basically based on the last 9 to 10 years, or 8 to 9 years of research. And it basically came from a figure that my very close chemist friend, Christoph Lamm from Vienna, showed me at one point. He showed me this pentose phosphate pathway, and some of you might know that already if you have some biological background. It's basically 6 molecules with 5 carbons included, the red ones, that are via this mechanism that you find in all kinds of teaching books, translated into 5 molecules, which are the green ones, which have 6 carbons. And the idea was, shouldn't there be more possibilities, and shouldn't we make a systematic approach to do this? And at that time, there was a very clever master student, Jakob Lykke Andersen, and that's the story of 9 years of work then, and hopefully I can show you that we kind of solved at least this problem. So the presentation that I do now here is kind of an overview to a certain degree, and for those that saw me speaking before, there will be hopefully also something that you haven't seen before that will be kind of in the last few slides. But this is kind of our modeling approach to chemistry, right? And the core idea will be that the entities that we have when we model chemistry are, the atoms have an identity. So we will be able to trace individual atoms through sequence of reactions, right? So the model will be graphs, molecules will be graphs, and similar like formal languages in computer science, you might know this, where you rewrite strings, right? And you get new strings, and you want to know which strings can you create. Similarly, we do something with graphs now. So we allow graphs to somehow react, and you get new graphs. So you get a language of graphs, so to say, which will then be the chemical space. Formally, this will be a directed hypergraph. And on that step, the chemical reactions will be graph transformations. That's here. Then we will have this large space, right, which is kind of over-approximation of things that will be happening, because at that point, we didn't include any thermodynamic constraints or something. And within this large network, we are then looking for certain patterns. For example, can you create a specific compound? Is there an autoclitic pattern in this network? And so on. That will then formally be integer hyperflow, which we can subsequently then analyze with other methods that I will briefly introduce you to. We applied this already to a certain chemical or biochemical systems. Everything that you will see here, and hopefully you will see also during the presentation, the tool, everything is implemented because the implementation, so it should be usable to chemists. So it's not just meant for a theoretical result, but in the maybe not too long run, we hope that this really has impact. And yeah, so that's the overview. So everything, when you have a chemical reaction network or a biochemical reaction network, and you have a combinatorics of compounds, and you want to understand the individual traces of atoms, there the framework can be applied. That might include, for example, mass spectrometry, or what you will see also, the hypothetical pre-periodic chemistries or metabolic engineering, whatever you like. You have a large chemical space, you want to understand or design something. So the idea, right, of modeling molecules as graphs is Stone Age old, right? So this is from the 19th century. I find it always interesting and worth to underline that the term graph in the scientific sense actually comes from this paper from Sylvester, Chemistry and Algebra. So where the math was already quite advanced, using generating functions to do all kinds of tricks in combinatorics, and the chemists were on a level where they were in the phase of defining what is a molecule really, right? And the term graph, actually also the term tree, was first used in this context, right? So if you have a graph theory background, there's the root. So, but it's very simple, right? Our molecules are simple labeled graphs. We have labels, right, which of course reflect the atom type, and we have labels on the edges which reflect the edge type. Now, forget K here for a second. Just look at L and R. This is how we model a chemical reaction. So it's basically, and we'll show this maybe already in the next slide, and come back to that slide. So here you have two chemical compounds, right, and there might be a reaction that somehow merges these two compounds into this compound. Here are, again, two chemical compounds. Note, this is not the same compound as this one. But the chemical reaction that you see here is basically the same. So if you would highlight it, you see the blue part here is exactly the same. So by that, you can, so to say you want to find a pattern. If you find that pattern, you're allowed to apply a graph transformation, and you get a new compound. So formally, this is the so-called double push-out approach, and what you see here on the top is the illustration of a chemical rule. For now, it's fine if you just think this left-hand side needs to be found somewhere in one or a set of compounds, and then it's rewritten into this thing, and you might create new compounds. So let's, right, this is, so to say, rule application then. Here's the pattern that describes the rule, so L and R. So let's assume we have thousands of compounds, and you choose two of them. For example, here, this compound and this compound. You look if you find a match. So that's a subgraph morphism matching problem. So you find a match. If you find that match, so you check, you are allowed to apply the rule. You make the rule, and you create a new compound. That's why we call it generative chemistry, because we don't go to a database or something, but in an iterative fashion, we just create those rules. Let's make an example. So this is the running introductory example for me. So you have formaldehyde and glycolaldehyde, these two compounds. That's what we will start with. And we just take 4 rules. very simple rules. These rules, as you can see, just change internally something within a compound. No, these are patterns, right? These are not chemical compounds. It's only the pattern that you need to match. And this rule, for example, will merge two chemical compounds, and this is the inverse of it, and will split two chemical compounds. So if we use these rules, maybe let's just do this. So we start with formaldehyde and glycolaldehyde, and we just say, let's apply all the rules over and over again. So the only thing that you can do here is actually apply a rule to G1. If you apply a rule to G1, the only thing that you can do is such a tautomerization reaction, you get this compound P0. Now you can actually apply this rule, because now you have a C double bond OH and a C double bond O, and you can rewrite it into this. So here you have a C double bond OH, and you have a C double bond O. So G0 and P0 can now react. So you apply that rule, G0 and P0, now via this reaction, R2, which is the aldol addition, you create this compound, right? And now this reflects a chemical reaction which merges two compounds. That's why this is the structure that you see here is a hypergraph in contrast to a graph, because it's not a connection between a vertex and a vertex, but between a set of vertices and a set of vertices, a multiset actually. Okay, so if you do this again and again, the whole thing grows, right? Grows combinatorially, very large. I skip the demonstration 1 and go to demonstration 2 because this will include demonstration 1. But this hypergraph, right, this corresponds to a chemical space, and we might want to look at something interesting in this chemical space. So for example, can you create, having only formaldehyde, can you create glycolaldehyde? Or can you, if you have a glycolaldehyde and have formaldehyde, can you create a second glycolaldehyde? Something like that, and you might want to analyze these things. Indeed, you can do this. So you can formalize this in mathematical terms and then take this large chemical space and, for example, formulate that question actually via integer linear programming. You can say, given two formaldehyde and one glycolaldehyde, how can a second glycolaldehyde be produced? The solution that you will get then is exactly the solution that you see here. And maybe this is now the point where I can just show you, right? So this is literally the code. Sorry that I throw you directly into code, but it's relatively easy. So I load the grammar, which is basically an encoding of the grammars that you just saw in text form. Here I expand the chemical space, just saying, well, just expand, don't make too large molecules. And here's then the essence where I just say, well, find me an autocolytic pattern, right? I could also write here something like, given formaldehyde and a glycolaldehyde, find me a second glycolaldehyde. If you do this then, so I literally let it run now. You see now it's done already in creating a PDF report, but you see already here that there's a solution, and this should only take 3-4 more seconds, I hope. Yes. So what you are given then is a nice report where you then see the graphs that you loaded in the first place, right? This is all auto-generated. So the formaldehyde and glycolaldehyde were loaded in the first place. Here are the rules, right? This is, for example, the ketoenol isomerization reaction. And then and what you also find is a flow solution. And that is exactly the solution to what I asked. So I created this large chemical space. Let me just look for the derivation graph. Where do I have that? The derivation graph is here, right? So I expanded the chemical space. This is relatively small, just for illustration reasons. Then I asked, can I find in this chemical space an autocolytic pattern? And the solution for that, the solver says, yes, there is an autocolytic pattern, and it looks like that. So you are indeed taking a glycolaldehyde. So this is the F1, means you plug one in. Then you go here. Then that reaction takes this and a formaldehyde, creates this guy. This guy gets this guy takes a second formaldehyde, gets this guy, gets this guy, gets this guy. This guy splits in two compounds, and then this compound goes here, and you get two glycolaldehyde out. Why is this important? If you have some background in life science, you should probably know that. If you have a pot full of formaldehyde and you throw one glycolaldehyde in, and that would trigger the creation of a second glycolaldehyde, those two will do the same, so you get an exponential growth, which is the autocolysis, but you need glycolaldehyde in the first place. Right, so this is kind of the overview of the system. And the nice thing is, of course, we didn't connect to any database. Of course, there's things missing so far, what I told you. There's no thermodynamics, for example. But we can now enumerate also solutions. It means it's math, it's programming. So we just say, well, give me not one solution, but give me 1,000 solutions, right? Here you see, for example, an illustration of one of the solutions that I just showed you, the glycolaldehyde running around the cycle. You create again a glycolaldehyde, but also a second glycolaldehyde while consuming 2 formaldehydes. Now you can suddenly analyze things like, well, can the fact that you trigger that solution, right, that this chemistry is running, maybe trigger another solution. So here you see indeed this green compound is given as a borrowing mechanism to this cycle here, and this cycle can then start also in autocalytic fashion create glycolaldehyde. So you see, so not now specifically analyzing the Formose reaction, this is more like how we approach analyzing chemical systems, and maybe also to the pentose phosphate pathway that I started with, and maybe show you that also. I think there I prepared because I just didn't want to. You see, I did that well recently, but you see here I do exactly the same thing again. So I just define a set of rules, right? These are now biochemical rules. So for example, this is a chemical rule, aldose, ketose, forward reaction. I expand the chemical space again. Somewhere there will be the derivation graph. Let's not look for it. I don't know where it is. But then you can ask for a solution, and the solution then will exactly do something like, okay, you ask for, given 6 of those, how can I create 5 of those? Okay, and the mathematical tool took the large chemical space, you make the mathematical question, you get this thing out, and this solution, which is formally an integer hyperflow, illustrates how 6 of those compounds, actually 2 go here, and then you have 4 here and 2 here, then 2 of those and 2 of those react to 2 of those and 2 of those, and because these figures are not very much liked by chemists, I just do a subsequent Petri net analysis. Let me do that, and this is, I think I do it, Ml minus F. So I create a derivation graph, then I create the pathways, and then I do a Petri net analysis, and if I do this, then this should only take a second. Because this flow solution doesn't really give you the order of the individual reactions happening. And if you, I forgot the number that I want to look for. Yes, so if you do a subsequent Petri net analysis, then you get a figure like that. And that is literally the PPP pathway as you find it in the school books. Time now goes top down, right? Now suddenly you have multiplicities of the same compound. So this basically explains to you now what's happening. So the ribulose 5-phosphate makes a reaction, get this compound, this reacts with this compound, and so on and so on. And if you go via time, you will see how your gold compounds were created, right? So this is literally the solution that you just saw, but there are also many other solutions. So I don't use time for it right now, but you might also get a solution like that, that overall also takes the same, the overall reaction is the same, but for example, here you needed to borrow a specific compound in the first place, so it needed to be there. So and if it's there, then you can run the reaction mechanism, get the same overall reaction, and you're given back the compound that you borrowed in the first place. So things like that we can analyze. Also another brief introduction, a hypothesis by Eschenmoser, how you get from hydrogen cyanide compounds, pre-periodic Earth atmosphere full of hydrogen cyanide. How can you go to biological compounds? His hypothesis was that you basically have coupled autocalytic cycles. So here you have a hydrogen cyanide compound, which in an autocalytic fashion creates this compound. This compound then reacts as a food compound for a second autocalytic cycle, and this compound then is a precursor for biological compounds. That's a hypothesis by Eschenmoser. So what you can do is you model the very complicated chemistry of pre-periodic Earth, or what we have as hypothesis right now, expand the chemical space, and then look for patterns as you just saw. And that is in a nutshell, the solution that you would then see. And you see here, indeed, via hydrogen cyanide as food molecule, you create here in autocatalytic fashion the glyoxylate. The glyoxylate then reacts as a food molecule to a second autocatalytic cycle, which you will see here. And the oxaloacetate is, the oxaloglycolate is produced in a second autocatalytic fashion. So this is kind of the way how we try to analyze the systems. We have objective functions, right? So what do you want your solution to look like? Usually we say, well, a small, short explanation would be nice, right? But you can also include things like thermodynamics in the objective function, such that you say things like, give me a solution which is consistent to certain thermodynamical properties, so that you can also do everything you can formulate in a linear fashion is very nicely integratable. And you can attach any kind of attributes to compounds or reactions. That's kind of the idea. Okay, so what you just saw is how we model molecules as graphs, chemical reactions as graph rewrites. We create a gigantic, often large directed hypergraph. We use this flows, that's a generalization of flows in graphs. It's called an integer hyperflow in order to find pathways. And then we take these pathways and further analyze them, for example, with respect to atom tracing, or without giving you a deep introduction, using Petri net analysis in order to see in which order things need to happen. Right, and everything is also online available, but I showed this in one of the next demonstrations. What I will speak now about is a bit more detail about switching of abstraction levels, because this is kind of a very important thing, in my opinion, and then a specific topic on multi-enzymatic design, and in the last few slides, something that hopefully neither Shaw or Walter really has seen so far. Okay, right. So what are computer scientists, you might ask? So because I'm a computer scientist, I don't have training in biology or chemistry. I have all my knowledge from my chemist friend from Vienna or from Peter Stadler, or going through literature, so I fight my way through. Computer scientists, actually you might know this guy, Donald Knuth. He actually says the psychological profiling of a computer scientist is mostly the ability to shift levels of abstractions. So when we see systems, we always try to think, how can we shift abstraction levels? And you want to answer the question that you want to answer on the right abstraction level, right? So here you see, for example, I think I even have the web page for that open. That's a beautiful web page where you can just write here some C++ code, and you have in real time the assembler code for that created, right? So this is what your CPU executes, these instructions. You don't want to program in assembler, right? So this is a mess. You want to describe your program on a higher level, right? You might even not want to describe it as a program. You might want to say, I want to declare a problem. The declarative way how I define my problem creates code. The code is then mapped to a lower level on assembler. So we always try to switch around in these different abstraction levels. And that's actually very much related to what you will see now, because I try to use the graph grammar approach in order to switch abstraction level. So importantly, without going to the category theory underlying it, but that's a mathematical area called category theory, and a graph transformation is an operator in a category. So what does this mean? You can think about it like you have a plus operator, +3 as an operator. So in integers, you can say +3. You have another operator that says +4. Of course, you can compose these two operators, namely you have then a +7, right? So in a category, one of the essential things is that you have an operator, and the operator is composable. So, and if we write, and that's what you saw already, the transformation as an operator, then we know if we're in category theory, we can compose it, right? So I make a very simple example. So assume, this is now close to trivial, but assume you apply a chemical rule, and you know that that chemical rule will make a precondition for a second rule, always. So it will just ensure that what you create makes sure that you can apply a certain second rule that you have. That's what I explain here, is a full rule composition. So the first rule is a rewrite from L1 to R1, and the second rule is a rewrite from L2 to R2. And we just assume now for a second that R1 will always ensure the precondition for the second rule application. Well, it's trivial that you can then compose those two rules. Here I make a chemical example, right? So here this is the first rule, which is chemically not very sensible because it does nothing. It's the identity chemical rule. So these two compounds are rewritten into these two identical compounds, but I just want to make the point clear. Here's the second rule, which is indeed a proper chemical rule. So this subpattern is rewritten into this subpattern. You know, of course, if you apply the first rule, you will always create this specific subpattern, which is a precondition for the application of the second rule. So you can compose the rule and you get an overall rule. So that's very important because you can now say, well, you have a sequence of graph transformation rules, you can compose them, right? It's more complicated if it's not a full transformation, but in essence, that's it. So what you can, for example, now do, we looked at a rule composition. I showed you how we find the solution. Now you can make a Petri net analysis and see in which order the specific rules are applied, and then you can just compose those rules, right? So, and this is where I go to our framework here. Let me make it a bit larger. Right, so you can just go to the web page, and there's examples, and one of the examples says rule composition overall for Mohs reaction, and that's literally the sequence of application of rules that you saw, right? So, and this is a composite operator, so without looking into the details, but this is basically just the expression for compose this rule with this rule with this rule with this rule. And just look what the overall thing is. Well, the overall rule must be a rule, right? So you compose rules and you get a new rule. And what you get actually is not just one rule, but you get a set of rules. And well, what does the for Mohs reaction do? It takes two formaldehyde and a glycolaldehyde, and it creates two glycolaldehydes. So via going through these 10 rules, if you compose them, then you get actually 4 overall rules that have that pattern. And here's, for example, 1. This is now a composed rule, right? Like combining +3 and +4 as an operator. That's the rule. Well, no surprise. You have a formaldehyde, and a glycolaldehyde, and they are rewritten into glycolaldehydes, right? So, but what we did now is, so to say, what chemists like to do, you have individual steps, and we have an overall reaction now, right? But you get not only this, you also get 4 others. The 4 others will, of course, do the same thing. They will also take 2 formaldehydes and a glycolaldehyde and will create a second glycolaldehyde. But the atom traces are different. So here, this carbon might end up wherever. In another rule, it might end up somewhere different. So the overall atom trace is different then, right? And that's, of course, important. So, and everything is automatic here. So that is the rule composition. And right, so you can, just to illustrate it again, this was from this Eschenmoser example that we analyzed earlier with the prebiotic chemistry. Here you have a compound. This compound should be hydrolyzed, and you use this compound here as a catalyst. Basically, this is a sequence of 4 rules, now not left, right, but top, bottom, so to say. This is the rules. And what we do is we compose the rules. So this is just the same as this rule. Then we compose the first 2 rules. You get this overall rule. You compose the first 3 rules. You get this overall rule, and so on. And then you get the overall rule, which looks like that. So you should have the idea of, okay, they basically do math with chemical reactions, and you can compose the mathematical operators. So that's that part. So how can we use this? Let me show you a pathway that is quite interesting. You might know how you get from glucose to pyruvate. So if you eat sugar, right, you create 2 pyruvate molecules. These are these small molecules here. Those actually then later stack up and get fatty acids. You find them here, right? So this is kind of the from sugar to fat, right? And we stop earlier here. But there's different ways how we can do this, or what different species implemented. Either the so-called Embden-Meyerhoff-Parnas pathway, EMP, or the Entner-Dudorov pathway, right? And I will briefly show you here. If you have here this sugar-like molecule, or this comes from sugar, then you can either follow now the green arrows or the black arrows. So let's follow the black arrows first. So if we go by the black arrows, then you will see you end up in the end with these two compounds. All these are identical compounds. These are the pyruvates, right? So if you would follow the black, I don't know if this is the EMP or the ED pathway, I forgot. But then you create those two compounds. If you follow the green arrows, then you will create those two compounds here, that and that one, right? So here's the green arrow. So if you want to know if a species has one or the other pathway active, right, we can use isotope labeling. You might know this technology. You take a compound. You basically can, as a computer scientist, we would say, color a carbon and look where it goes to, and then analyze your result and find out where did your label go, right? You basically put an additional neutron in the atom. So if you, for example, would label the carbon 1 here, right, what would happen? And now the atom traces are important, right? All our rules are accurate on an atomic level, so the atoms have identity, so we can follow the one through this sequence of reactions, and we find then, well, this one ends up here. So you would expect that you find in 50% of the created pyruvates a compound that is labeled at that point with an additional neutron, which you can analyze with all kinds of different technologies. If you would find the other path, follow the other pathway, you would might find out that this one, which is at a carboxyl group, is labeled, so that's different. So about the positioning of the label, you will then find out which of the two pathways was active. In contrast, if you would have labeled 2, for example, in the beginning, then you would end up that in 50% of the carbons going the black pathway, this guy would be labeled. And if you follow the green, this would be labeled. And they are the same. So you wouldn't be able to distinguish, right? Sorry, that's not, the rotation is, but they are all the same. And so what would this mean? This means that you have a handle on making automatically isotope labeling experiments. So if you have pathway alternatives, you, with this method, are able to say, well, you should better label this carbon and then look at your result where it did go in order to find out if one or the other pathway was active. So this is how you can use the composition, right? This is now really mathematically what we did, right? So you can write this down really in our framework. So, and if you compose them, then these are the two different overall reactions. That's basically what you just saw. Now yes? No, you can do as you wish. I mean, I don't know if this is a computer science question or a chemistry question. Well, I'm not a chemist, but how I understand it, if you say in one specific compound you want one specific carbon labeled, then it's getting expensive. So it's a matter of price, and often you say, well, you get a certain distribution or something like that. So that's how. But conceptually, you can think about you label a specific carbon. Okay, so this was the atom tracing. The next thing I want to speak about is about actually multi-enzymatic design, something that we worked on. And that's also something that I, in the last half year, had the pleasure to discuss also with Walter every now and then. So enzymes are very weird compounds, in my opinion, the more I think about it. So these are these large molecules, and you probably know this. They are basically proteins, somehow folded. And then they are very specific. So a small molecule goes into the enzyme. Then in a multi-step of chemical reactions that are basically triggered by the amino acids that are sticking out in the reactive side, your compound that went in is somehow translated, and the enzyme remains unchanged, and the product is released. So that's quite fascinating, right? The enzyme is in the same state before as when the compound went in. So it's a catalytic cycle that it triggers. So that's something that where we are trying to kind of understand. Well, you basically in the actives, a protein is complicated because it's a lot about stability, but the active side where a compound is really changed there might be 3 to 5 amino acids or something like that that are involved in making the change, right? It's not that this long chain of amino acids, which is mainly due to stabilizing the whole structure, is really used. The real chemistry, in the real chemical changes of an educt, only something like 3 to 5 amino acids are involved. So they're quite interesting, right? And we are trying to be kind of take a step back. Let's assume any 3 to 5 amino acids. So what can we do, right? So that's kind of, but this is very early phase. And what I rather want to speak about is if you would not just design one enzyme, but you have a system like the following, where multi-enzymes are involved. So that's a paper that I think Christoph at one point found in 2013 from Bogora and Liao and colleagues. So this is again, right, our favorite compound that comes from the sugar. And here we create our 2 pyruvates, which make the fat, right? So here we have energy. So these 2 pyruvates actually create this so-called ASCO-R compound, which is kind of the energy in our body, right? So it's kind of interesting that here in this compound you have 6 carbon atoms. So this compound here has 2 carbon atoms, and you create 2 of them. So you only use 4 of the carbon atoms from the sugar. 2 are actually lost via the carbon dioxide, okay? So those guys thought, well, we want to make a carbon-efficient alternative for this so-called glycolysis pathway. So they said, okay, can we design something where we don't lose the carbons via the carbon dioxide? And they kind of engineered it, right? So they said, okay, if we use a specific set of compounds and we design this green box here in a clever way, namely like that, then we might be able to design glycolysis, so the same overall reaction, but without losing carbon dioxide, right? So, well, that's exactly what we made our tool for, right? We just say, okay, have a certain set of reactions, right? An enzyme corresponds, so to say, to a reaction that you can make. And then you take a step back and say, expand the gigantic chemical space and try to find a solution, right? Just ask the tool, give me a solution that does not lose carbon, right? Because you can implement that and ask that in a mathematical question. That's from their paper, right? Where they kind of designed, based on a certain set of enzymes that you're using, which reaction mechanism with multiple steps of multiple enzymes is implemented to create these ACP compounds here. Okay, so we modeled the rules. It's actually not that many. Then we just say, well, this is now exactly, this is really the syntax, right? So you basically say, okay, throw these 5 compounds in your virtual pot, then apply all rules that you have again and again and again, make a large chemical space, right? So you create a so-called derivation graph. And then you basically ask the question of, okay, you are given this compound, which is our favorite sugar compound, the F6P, and you say, I want to create this compound, which is this energy-loaded compound, ACP, and then you just ask for, find me a solution that does that, right? And of course, what you find is, for example, the designs of what they did in their paper. So they had 2 or 3 designs in the paper. They are labeled here by A, B, and C. So what you see here in this table is possible solutions. We just enumerated them. So if you see, for example, 24 here, this means it's a class of 24 different solutions. Without going into the very details, but they are now classified with respect to which kind of enzymes you are using. And so some enzymes are specific to compounds that have 5 carbons or 6 carbons, and you might use only a specific class. And you see it's a hypothesis generator for metabolic networks, so to say, so metabolic engineering. So the dream being whatever. We want to create a species that makes whatever oil out of plastic. So let's design it, so to say, right? So that's the dream step forward here. Okay, it's here just for illustration reasons. You see then the guys in the science paper actually, so this is not just a theoretical design, they did it in a petri dish and they get a yield of something like 99% or something like that. So it's really working, right? No carbon dioxide loss. Then the next step is, of course, that you create a species, so you modify some whatever species, that then creates the enzymes, that then triggers this reaction step. They were reasonably successful with that, but this is, I would say, work in progress as far as I understand, but I find it extremely fascinating. And that's just different hypothesis solution that we find, and yes. Okay, so that was the second step. Now the third step, which is, well, really work in progress. Some figures that you see here now are really just created in the last week or something. I thought I'd make at least something that is very new. So this figure here is a nice illustration for me for two reasons, right? You might already sense, well, the modeling of the graph grammar rules is really essential, right? I mean, if you do a mistake there, you mess up everything, right? So you need to make your modeling of a graph grammar rule very accurate. And this one is a nice example. That's the so-called unrock mechanism, where you have this compound, which is translated into this compound. And if you, there's tools out there that try to predict you what is happening via a specific reaction with the atoms. And most often these tools look at the graphical structure of the educt and the product side, and they assume like the maximum common subgraph or a small number of changes is a reasonable explanation. So this is a very nice counterexample for that. You have this compound here, and you basically just need to cut this bromium here away and add it at this NH2 group here. You might think that's how the mechanism really works. Well, it's very different. Actually, what's happening is you first open the sixth, so you have ammonium, so the NH3, that attacks this carbon here, opens the cycle, those N and bromium then rotate, and basically the nitrogen that came from the outside is then included in the sixth ring. So you see the pathway here. So you go from here to here to here to here, and then the nitrogen here is the new nitrogen. How can you verify this? Well, with labeling again, right? Here, to your question, it's relatively easy to just label all nitrogens, right? So here, and this is how this is verified, that it's really this mechanism, because you can just label all the nitrogens of the educt, make the mechanism, and then see that only half of the nitrogens are labeled in the gold compound. Okay, so this is something that I literally started with a PhD student while being with Walter in Boston, because what you can do now is, so here's an illustration of the wrong mechanism, right? So we just cut off the BR and add the H2N. Sorry for the rotation issue, it doesn't matter. Ignore the dotted lines for now. And this is the correct mechanism, right? So you go via a ring opening and then and so on. So let's assume now, this is actually strongly connected to an area called semigroup theory. And there's a lot of theory in decompositions of semigroups. So Krohn Rhodes are two of the main driving people there. And I looked into that, and one of the things that they are doing, just assume now all the atoms have a number, okay? So for example here, and I look now, for example, only at the nitrogens, and I give them the label 2, and I give this one the label 3. So what can happen then, right? So you actually, the 2 and the 3 via this reaction can be mapped to a 5 and a 6. So this is the 2 and the 3 can go to a 5 and 6. So you see 2, 3, 5, 6, continue, 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 and then the two labels can end up at position 14 and 15 in the gold compound. And if you would go via the wrong mechanism, then you would end up in 14 or 13. So group theoretically, you can express this as a so-called Wright-Cayley graph of elements. And the nice thing is, of course, that if you now make certain predictions, right, then you say, well, either the two labels end up at 14, 13, so here and here, so both are still in the ring, or 15 and 14, so which is here and here. And these things you then can again verify via all kind of different techniques like NMR spectroscopy or mass spectrometry, and kind of verify which mechanism was active or not. So taking this idea, let's look at a slightly more example, namely the TCA cycle, which is one of the main cycles in our metabolism, right? So let's again ignore the lines for now. So here's a starting compound called oxaloacetate. And this compound is shuffled around via 10 reactions and is produced again as oxaloacetate. There's much more to say about this cycle, Krebs cycle or citric acid cycle, however you want to call it. But let's take this simple version of it and let's do exactly the same that I just did here, right? Create the so-called White-Cayley graph. So, and I want to look now at 4, 5, 6, 7. So these are the 4 carbons here that we have. And if you now create the White-Cayley graph for this, it looks like this. So this is a bit more complicated. Somewhere here, if I would zoom out you would see this is 4, 5, 6, 7. And then you can run around and somehow, whatever, run through the TCA cycle. So this is difficult to analyze, so let's make the following. Let's look at, you look only at oxaloacetate. You can somehow then take the 4 carbons, you run around in the cycle, something happens to the carbons then. So let's only look at oxaloacetate. So this figure here, what you see here, is 4, 5, 6, 7. This is our starting compound. And when I draw an arrow now here, it means, well, I run once through the complete cycle, and the 4 is lost, right? So this means, well, the 3 carbons that you had on position 5, 6, and 7 are still there. It's the same carbons, and they ran once through the cycle. But that carbon here on position 4, which would, whatever that one is, this one here, right? This is lost, right? So furthermore, well, there are other possibilities. There's also the possibility that you run around the cycle and you lose 2 carbons, right? Because sometimes you have choice. I didn't illustrate this in detail so far, but when you apply a reaction, because there might be symmetries or you have alternatives, there's different possibilities. What I also highlighted here in this gray box, that's a so-called strongly connected component in this graph. What does this mean? This means if you're in a gray box, for example, you have 2 atoms called 5 and 6 in the oxaloacetate, you can run around the complete cycle and still have this still have these 2 carbons. So that's then a gray box. So if you don't have a gray box, for example here, you have no choice running around the citric acid cycle and still have those 4 compounds. So there's quite some interesting things to see here. So for example, you see, you can do the following. You have 4, 5, 6, 7. You can kind of take these 2 carbons and left shift them by 1, and you get then to here. So 6, 7, and the 2 outer are lost in this process. You can do this again. Now, of course, the 7 is moved 1 more to the left, right? And then you do it again, and of course, eventually everything is lost. So you see you have something like a shift operator on a carbon level. You also see something like that, which is 6, 5, 5, 6, meaning you can run around the cycle and swap the 2 inner carbons, right? So this is because we have a 6, 5 and a 5, 6. That's exactly what we automatically, that's an auto-generated figure. That's literally re-golded or something. But that's exactly what you see here. So from the 5 here, right, follow the blue line, zack, 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 and it ends up at position 6. And the orange line, zack, 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 ends up at position 5. So you are basically swapped the 2 carbons. Right, this is, I think, 3 seconds over now. The fields in science are arranged by purity. So these are the mathematicians, and here are all the other nice sciences. And I always try to sell this like we're trying to push ourselves somewhere here. I find it quite puzzling, right, that the overlap of biology and computer science is so strong. I mean, every institution in the world has a bioinformatics center, and so much has happened in the last 20 years. Chemistry and computer science, of course, there's also things going on, but it's just a different league, in my opinion. There are so many core results in computer science that didn't make it into chemistry yet, right? Which I find interesting and amazing, because there's a lot of apples hanging that one can just take. So, but what I introduced you to was this generative chemistry via graph rewriting, introduced you briefly to automatic coarse graining. Important is that our atoms have identity. So every chemical reaction network that you have where you need the identity, where the identity of a specific atom is relevant, you can hopefully handle with our framework. Final word to algorithmic engineering. So in theoretical computer science, and there's a lot of theory here behind what you just saw, the big conferences often present new algorithmic approaches for X, Y, Z. Often these results that are presented there are far from implementable, right? So if you would, for example, look for the best algorithm for matrix-matrix multiplication, actually you cannot implement it. So one of the leading scientists in that area called Rob Sedgwick, he calls them galactic algorithms because the constants are so large, right, that even though the asymptotic runtime says this is a good algorithm, there's no way you will ever be able to implement that algorithm. It doesn't make sense. So here, what you saw here, if you would now ask, so how many NP complete questions or P-space complete questions would you solve, right? I would tell you, well, thousands in a second, right? But that's not the point, right? So the point is you need a very good implementation of the things you're doing. And for example, the subgraph morphisms that we need to solve, which is an NP-complete problem, is not the limiting factor at all here, right? And that's what the area of algorithmic engineering in computer science, relatively new area, I would say, is trying to promote. Well, theory, please speak to the people implementing stuff, and the other way around, and try to bring these two worlds together such that the theoretical results are also impacting libraries or whatever. So, and luckily Jakob, who is a brilliant C++ programmer, is kind of the core developer here. All what you saw here is, of course, based on a team, mainly Christoph from Vienna and Peter Stadler from Leipzig, and the decomposition that you saw in the end, I mainly worked on with Nikolai Neugor, who's a PhD student of mine. Thank you very much.